In this video tutorial, we will discuss images produced by lenses. The behavior of light in lenses is very similar to the behavior of light in curved mirrors, so many of the key terms and rules will be familiar with you. But instead of reflecting light rays, lenses refract them. And just as we have convex and concave mirrors, we also have convex lenses and concave lenses. Now, a convex lens is also known as a converging lens because it forces parallel light rays that enter it to converge at the focal point on the other side. However, with curved mirrors, the focal point was on the same side as the object. But that's because the mirrors are not transparent. They don't let light through, they have to reflect it back. Now, another difference is that a concave mirror is also known as a converging mirror. This is because the parallel light rays converge on the focal point that is on the same side as the object. Meanwhile, a converging lens is called a convex lens, not concave. So they're kind of opposites in that sense. Now, these convex or converging lenses are thickest in the center and become thinner and thinner as you reach the ends. The other type of lens is called a diverging lens, also known as the concave lens. This is similar to the diverging mirrors we encountered, except again, instead of calling it convex, they are called concave. But both will diverge parallel light rays, spreading them out away from each other. And because these light rays spread out and diverge, getting further and further away, you have to backtrack the reflected rays in order to see where they focus, where they converge. Well, it's the same with the lens. These also diverge, getting further and further away, and you must backtrack the refracted ray this time to see where they converge at the focal point. Furthermore, diverging lenses are thinnest in the middle, but start to get thicker and thicker as you get towards the ends of the lens. So we call them diverging lenses because they start to diverge the light rays that are coming in parallel. So once again, they are called diverging lenses because they cause parallel light rays that enter to spread out and diverge away from each other, while a converging lens does the exact opposite, causing the parallel light rays to converge and come together at the focal point. Now, because this is an introductory course, we will be cheating a little bit and simplifying things to make things easier for us. As you learned in our previous lesson, when a light ray goes from one medium, in this case air, into another medium, in this case glass, it refracts, it bends. This is because light travels in different speeds in different mediums. And so a light ray traveling from air into glass, then back out to air, gets refracted twice. Once at this phase boundary between air and glass, and refracting a second time at this phase boundary between glass and air. However, the small amount of refraction that occurs in this area over here is usually too small to worry about as long as the lens is thin enough. And in all of the problems that we'll be dealing with, they will be very, very thin lenses. As such, we can do a shortcut where we pretend it only refracts once instead of twice. By drawing a dotted line down the center of the lens, we can pretend the light refracts only at this one location rather than at two locations. In the end, this little shortcut doesn't really change our answer much, but it does help us because we don't have to do two separate calculations anymore. One simple calculation will do the same job. Alright, so just be aware we are cheating a little bit, but the differences in our answers will be negligible. Now, if you recall, in a curved mirror, we had a center point, a focal point, and a vertex. But with a converging lens, because there are two circles, so one circle for this curve, and another circle for this curve, we're going to have two focal points. Where those parallel lines converge on the principal axis, we call that the principal focus, because the light rays actually focus on this spot. On the opposite side, we have the secondary principal focus. Now, the symbol for our principal focus is a capital letter F, while the symbol for the secondary principal focus is called F prime. So that little tick up here, the apostrophe, we call that prime, F prime. Instead of a vertex, we call this point the optical center. That's where our imaginary cheat line, the axis of symmetry, comes in contact with the principal axis. With a diverging lens, however, things are flipped. Because parallel light rays diverge or spread away from each other, they will never focus on this side of the lens. But if we backtrack on the refracted rays, we see that they also converge on the principal axis, but only on this side of the lens. And so with the diverging lens, the principal focus is on the same side as the original object. And because these refracted rays will never converge on this side of the lens, this now becomes the secondary principal focus, F prime. Alright, so diverging lenses are opposites of each other in that sense. Their principal focus and secondary principal focus switch places. So in summary, a converging lens, also known as a convex lens, brings parallel light rays together through the focus after refraction takes place. So only after the light rays refract through the lens. Meanwhile, a diverging lens, also known as a concave lens, spreads light rays apart after refraction so that it looks as if they have come from a virtual focus. So after refracting, they diverge away, but the only way to get them to converge together and to intersect with each other is by backtracking the refracted rays. Since these are not real light rays, the image produced will be virtual. Finally, the focal point of a converging lens is on the opposite side of the object, while the focal length of a diverging lens is on the same side as the object. Alright, so let's take a look at some of the rules of light rays coming in and how they refract out the different lenses. Rule number 1. As a parallel light ray enters the lens, it will refract through the principal focus. This is very similar to the rule with curved mirrors. Rule number 2. If a light ray comes through the secondary principal focus, so f', it will come out parallel. Again, similar to a curved mirror, if you go through the focal point, it comes out parallel. The hard part is that we have two focal points, and you have to enter through the secondary focus, not the principal. The last rule is the easiest. If you aim through the optical center, it comes out the optical center. Just like with a curved mirror, go through the center point, come out the center point. Now you notice with curved mirrors, they have a focal point and a center point. The center point distance to the focal point distance is the same as the focal point distance to the vertex. So these two distances are identical. Well, instead of a center point and a focal point, we now have an f and a 2f. But again, these lengths are identical. So the distance from f' to the optical center is the same as f' to 2f'. Now if you recall, we used SALT to describe the characteristics of an image that's created in a curved mirror. Well, we do the exact same for images created in lenses as well. So looking at this diagram, we see going through parallel comes out through the principal focus. Coming through the optical center goes straight through the optical center. And aiming for the secondary focus comes out parallel. And where these refracted rays converge, where they intersect, that's where our image appears. So this is very similar to what we did with our curved mirror diagrams as well. Now describing this image using SALT, we say that it is smaller, because we compare always back to the original object. Its attitude is inverted, because it's not facing the same direction as the original object. Its location is between f and 2f. And it is a real image, because these light rays do actually converge here. These are real light rays. So this is a real image. Now if we move the object a little closer to the lens, say at 2f', you'll notice that the image and the original object are now the same size. It's still inverted, so facing the opposite direction, and now it's located at 2f itself. And because these are real light rays that converge, it is a real image. I hope you're starting to see a pattern, because as the object gets closer and closer to the lens, you'll notice the image is getting bigger and bigger and bigger. So when it's between 2f' and f', it's now a larger image. It's still inverted. It is now beyond 2f, but it's still real because those light rays are still converging here. Now with curved mirrors, if your object was sitting at the focal point, there was no image produced because all the light rays are parallel. They will never intersect, not in the real world, not in the virtual world. Well, it's the same for lenses. Their refracted light rays will also be parallel and never intersect, not in the real world and not in the virtual world. Finally, with a converging mirror, if you move the object close enough to the mirror, say between f and v, the image now becomes virtual because the light rays start to diverge away from each other, so they will never meet in the real world. But if you backtrack the refracted rays, they do converge, they do meet together in the virtual world. Because light rays can't actually exist here, this is a virtual image. It doesn't actually exist. Well, the same is true over here. If you get the object close enough to the lens, its refracted rays will also start to diverge away from each other. Although they will never meet each other in the real world, we can backtrack the refracted rays and they will meet in the virtual world. We say this is virtual because the light rays coming from the object never actually meet each other here. They diverge and move farther and farther away. The real light rays will never interact with each other. Instead, our brains backtrack the refracted rays to a point where they converge, and we think we see something there that doesn't actually exist. So this is why it's called virtual. And this is how a magnifying glass works. When you bring a small object close enough to the magnifying glass, our brains project it back and think they see something bigger. So here we have a magnifying glass looking at something pretty small, like a stamp. Obviously a stamp is not this big, but our brains project it backwards to think there's a larger image than what is really there. So an image produced in this situation is going to be larger. It'll now be upright, so pointed in the same direction as the original object. It'll be behind the lens now because it's on the same side as the object, and it's virtual because the light rays never actually intersect here. On the other hand, if you look at a magnifying glass at an object that's far away, the image will be inverted or upside down. And that is what we see here. If the object is further away than the secondary principal focus, so past f prime, the image will appear inverted, upside down. So give it a try if you have a magnifying glass at home. If you look at an object that's far away, it will look inverted, upside down. And as you move closer and closer to the object, eventually the image will get blurry. That's because the object has reached the secondary focus and all the light rays are parallel, so no clear image can be created. But once your object moves closer to the lens, so between f prime and O, now you'll start to see the virtual image, which is larger and magnified. Alright, so here's a quick summary chart for what you should see when dealing with a convex lens. Now in a diverging lens, or concave lens, the refracted light rays will diverge, or rather move away from each other. Because they will never meet on this side of the lens, we must backtrack our refracted rays until they meet over here. Where they converge with the principal axis is called the principal focus now, and the other side is your secondary principal focus. So don't forget to flip f prime and f for this type of lens. Now with a diverging mirror, the image is always going to be virtual, so behind the mirror, upright, and smaller. Well, the same goes for images produced by a diverging lens. They too will always be upright, smaller, and virtual. Because how can light rays exist on this side if they haven't even reached the lens yet? So because our brains backtrack the refracted rays to create an image that doesn't exist, we say this image is virtual. Alright, so what I would like you to do now is try to draw these ray diagrams for lenses. We have the convex or converging lenses here and here, while the diverging lenses, the concave lenses, begin here and here. So follow the rules that we just learned and let me know if you run into any issues.